Okay, so last time we learned the Turan-Kubilius inequality and now they're corresponding to an additive arithmetic function there are certain quantities that we learned which are related to the average order as well as normal order of that function. So, e of x given any real number x greater than or equal to 2, e of x, which we also denote as e of x comma f, is defined as summation p raised to the k less than or equal to x. So, all the primes and their corresponding powers up to x, and the terms are f of p to the k over p to the k times 1 minus 1 over p, and d of x is defined as the following function. So, first we consider the sum p raised to the over p raised to the k less than or equal to x, and we take absolute of f of p raised to the k whole square over p raised to the k. This is the sum, but this is actually the square of d. So, we have to raise this to half. And what we learnt last time, although we proved it first, we proved it only for real valued functions which are also non-negative, but from that we know how to extend to real valued functions and more generally to complex valued functions. And I'll also leave it as an exercise in the next set. So, what we get is this very nice inequality. So, 1 over x. So, what we have is that there exists a function which vanishes as x goes to infinity, such that limit as x goes to infinity is equal to 0, and you have the inequality 1 over x summation n up to x absolute of f of n minus e of x whole square is less than or equal to 2 plus epsilon prime of x times d of x whole square, which holds uniformly for all x greater than or equal to 2 and for any additive arithmetic function f. So, uniformly now, as I had mentioned last time, this inequality has very useful applications in deriving normal orders of functions, but I would also like to mention before we move on to the application, for the most explicit example that we have when f of n is equal to omega of n, the prime counting function, we had seen that this sum asymptotically just behaves like sum of f of p to the k over p to the k. The second part minus 1 over p essentially became redundant if you were interested in the asymptotic growth of the function. So, what happens is this whole thing gets translated into a general format as well, So here is a small exercise for you, and this would be a good opportunity for you to actually practice the techniques we used to prove the Turan-Kubilius inequality. So instead of E of x, let us take a function which is related to it, and let's just call it A of x, which is basically summation over the same terms, but now we just take f of p raised to the k over p raised to the k. So we don't worry about the 1 minus 1 over p part. It turns out that a very similar theorem holds if you replace E by A, and that theorem is as follows: 1 over x summation n up to x absolute of f of n minus A of x whole square turns out to be less than or equal to 6 times d of x whole square. So in terms of the O estimate, this qualitatively, this is very similar to the previous theorem, but the constants here, the constant here is bigger than the constant you received here. But if you are only interested in asymptotics, then you don't necessarily care about the constants. So you may also choose to start with this function. So I leave the proof of this exercise, of this as an exercise. Now let me give you some very interesting consequences of the Turan-Kubilius inequality. So let us do the following. So let us take, as we know so far, our heuristic approach is to treat arithmetic functions as random variables on the probability space defined by the first capital N natural numbers, and then we see what happens as capital N goes to infinity. Now what we do is we partition this set into two parts. The first part, we just take something, we terminate at some point whose growth is much smaller than capital N. So we terminate at some function of n which is not only strictly less than n, but which is little o of n. Okay, so one possibility is n to the half, or you could actually take n to the theta. You may also consider, sometimes something really tiny, so you would wonder if you can take some power of log. Okay, there are many candidates, and I'll explain why we choose these types of candidates. And of course, this is the greatest integer of n to the half, since we are being precise. And then you have the remaining part between n to the half and n. Okay, so now what is the reason we are breaking this up into smaller parts? So here is an observation. Suppose we take reciprocals of the primes lying between root n and n. So let us take all those primes p which are strictly greater than root n and less than or equal to capital N. What should this be? Can you give me an estimate for this? Now this is a sum that we spent a lot of time studying. So this is basically the sum of all the reciprocals of primes up to capital N minus sum of all the reciprocals of prime up to square root of n, and therefore we already know how those behave asymptotically. So log n plus O of 1 minus log root n plus O of 1, which gets absorbed in the error term that we've already written. Now what is this difference, log n minus log root n? log root n is half of log n, and half of log n, log of half of log n is log n minus log 2. So, log of root n is also log of n plus O of 1. And therefore, what you end up getting is, this is just bounded above by some absolute positive constant. Okay, the main term log n and log n will cancel each other. So, this is something that we wouldn't have been able to do if we had taken, instead of root n, if we had taken some power of log n. Because then you would have had log n minus log n. They are different in orders. Okay. However, if you had chosen any n to the theta, the same thing would have gone through. So, why is this useful for us? So, here is what we observe. Let us take root n to be less than little n. So, let us choose any little n in this set which lies in the latter part of this set. Then, what can you say about the difference between E of n minus E of little n? If n is in this part of the set, what can you say about the difference? So, by definition, what is this set? This is the absolute of all those prime powers which are strictly greater than little n and less than or equal to capital N, f of p raised to the k over p raised to the k times 1 minus 1 over p. So, this is certainly less than or equal to summation absolute f of p raised to the k over p raised to the k. Okay, 1 minus 1 over p is less than or equal to 1. And what's more, since this n is something greater than root n, and once you put absolute values around this, these are all non-negative terms. So, this is certainly, the above is less than or equal to root n less than p to the k less than or equal to n. Now, I am going to write p to the k in the denominator just as we did in our previous class, 1 over p to the k by 2 times 1 over p to the k by 2. And now, after interchange of summations, what is our second most favorite technique in this course? Cauchy-Schwarz. So, we apply the Cauchy-Schwarz inequality and we get what is the first part. Absolute f of p whole square over p to the k raised to the half times summation p to the k 1 over p raised to the k, the whole thing raised to the half. Now, this is certainly less than or equal to, if you add more terms to it, the inequality will still hold. So, what this tells us is that this is less than or equal to. So, what we have is, okay, let's write it this way: absolute E of n minus E of little n whole square is certainly less than or equal to d of n square times summation p raised to the k, all the prime powers lying between root n and n 1 over p to the k. Now we saw before that in this sum, the dominant contribution will come from 1 over p. All those cases when k is exactly equal to 1, because when k is greater than or equal to 2, what you have is a sum which is contained in a bigger sum which is absolutely convergent. So the part of this sum where k is greater than or equal to 2 is just sum O of 1. So it's what happens when k is equal to 1. We just showed that if p lies in suitable intervals, then the main terms just vanishes and again you are left with something which is absolutely bounded above. And so with that choice at which to divide your interval, your set of numbers up to capital N, what you end up getting is absolute E of n minus E of little n whole square is less than or equal to, or rather less than d of n whole square. It's d of n whole square times something which is O of 1. We are all set, right? So far so good. Now, why are we doing this? You see, the reason why we are studying these functions E of n and d of n is to understand the average order and the normal order of a function. Now, when you consider in the set capital from 1 to capital N, and you consider, so capital N is the largest element in that set, whether you consider E of capital N or you consider E of little n, where n lies in that set from 1 to n, what exactly is the difference between the two? For a typical integer lying in the set 1 to n, how far does it deviate from what you consider the expected value of the function? This is what this quantity is trying to measure. And so this is a bound that you have. This can be expressed in terms of d of n square. So let's call this equation A, and we note this observation. We will come to it many a times. Now here is a small lemma. Suppose your additive arithmetic function is such a function such that your capital D of n is little o of E of n. Suppose this were given to you, that this right hand side in fact is little o of, its growth is much smaller than E of n. It is little o of E of capital N. Then what can you say about this? That would imply, then our claim is that E of little n is pretty much equal to E of capital N. Okay, so our claim is that E of little n is equal to E of capital N plus little o of E of n for almost all the integers lying between 1 and capital N. Okay, for a subset of integers in so let's just write the short form, since we are interested in what happens as capital N goes to infinity. So for almost all integers, and when I say integers, of course I'm referring only to positive integers, as capital N goes to infinity. Meaning this, as capital N goes to infinity, this asymptotic estimate holds in a set of integers, in a subset of natural numbers whose natural density is exactly equal to 1. The natural density. That set itself may not be all of n, but it will be almost all of the set of natural numbers. Okay. So how is this implied from Turan-Kubilius inequality? So again, this is similar to an idea that we had used in the proof of the Hardy-Ramanujan theorem, which by the way we are going to state in a more general form today. You see, so again, so this is true, if in case this is causing any confusion, this is true only when little n lies between square root of n and capital N. Okay? Okay. Now the thing is, how many integers are there up to root of n? It's O of root n, which is little o of n, right? So what that means is, so in the set, so here's the proof. So in the set, okay, up to here, the number of integers up to here is little o of n, because it is at most n to the half, and between this and this we have just shown that a holds. Between n to the half and n, we have shown that a holds. And therefore, if d of n is little o of e of n, then this holds as well. Okay? So let's call this b, and this implies that b holds. If we are given this condition, this is an important hypothesis. If the what you would consider as the term that shows up in the variance of an arithmetic function about its expected values, if it is much smaller than the expected value, then we have an equality of this form. And therefore, now suppose b does not hold for any integer in this range. It does not deter us because there are very few integers as compared to capital in this range. Okay? And therefore, this implies that equation b holds, okay, for almost, or rather for a set of natural numbers with natural density 1. Okay. So when you talk about E, which is related to the expected value of your function, so that this function that you defined as E of x, whether you consider some little n in the set in which you are working, or you consider E at the largest element of that set, the difference between them is very small if this asymptotic holds. Why is that useful to us? So this leads to normal orders of the functions that we are talking about. So let's make another observation. So recall the Turan-Kubilius inequality. What does it tell us? 1 over capital N summation n less than or equal to capital N f of n minus E of capital N whole square is less than or equal to, or rather, if you are not worried about the constant, then it's less than d of n whole square, which we know. So if d of n is little o of e of n, then the above inequality implies that 1 over capital N summation n less than or equal to capital N f of n minus e of n whole square over the whole thing the square of this ratio is going to 0 as capital N goes to infinity. Now, in the previous lemma that we just stated, you are telling me that almost everywhere E of little n is almost, it's very, very close to capital E of n with a very small difference between the two. So, combining this, so here is an exercise for you, just fill in the details, combine the above with B to deduce that if I replace E of capital N with E of little n, then the same asymptotic would hold for almost all numbers n. This over E of n whole square goes to 0. And last time we saw that if we have an asymptotic like this, that will immediately imply that E of n is the normal order of f of n, and therefore E of n is a normal order of f of n. So, this is how you use the Turan-Kubilius inequality to derive the normal order of an additive function. Always remember, the Turan-Kubilius inequality holds for additive functions. Now, let me make another observation. Since the entire motivation for all this work was what we call the Hardy-Ramanujan theorem, let me just state that in a more general form, and once I state and prove that, I will give you references to literature that now you will be able to study and understand. So, there are many Hardy-Ramanujan theorems, but this one states the following. So, let us take any function xi of n which goes to infinity. So, it explodes, it's a fast growing function as capital N goes to infinity. Okay. Now, the claim is they were of course interested mainly in the prime omega functions. So, they claim the following. So, the number of n less than or equal to capital N for which omega of little n, that is the number of distinct prime divisors of little n, minus e of this function, which we had seen asymptotically is log n, the claim is that the number of little n for which this is greater than xi of n over root of log n is very small, is in fact less than n over xi of n whole square. Okay. So let us see what is this actually leading to. So if you recall, what the Hardy-Ramanujan theorem was doing was, it was basically evaluating the variance between omega of n and its expected value log of n, and it was giving an upper bound for the variance. So this is just making that sharper. Okay, so variance was of the order of root, the square root of the variance was of the order of square root of log n. And so what this is doing is actually a sharper and a stronger version of that. So let's just go back to the Turan-Kubilius inequality and see what it says. Okay, so by the Turan-Kubilius inequality, what we have is that 1 over capital N number of, actually not the number, but if you take summation n less than or equal to capital N absolute of omega of n minus log capital N, apply it as we had stated it, this is less than or equal to some constant times log n. So this is less than. So in other words, what this is telling you is that 1 over n, suppose I bring this back to the left hand side. So what we have is summation of little n up to capital N omega of n minus log n over square root of log n whole square is less than 1. Okay. Now what we do is, we are taking any xi of n which is increasing. Okay. So what this means is that, suppose I put 1 over n times xi square of n, I put this in the denominator, because it is also growing quite fast, you will still have over square root of log n okay, this whole square would be less than 1 over xi square of n. In other words, I can actually take capital N to the right. And this will imply the theorem we are after. Okay? Because if there were too many of these n's, then when you add up this quantity for all the n up to n, it cannot possibly be bounded above by n over xi square of n. So what we have proved is actually a stronger version of what we require. And in the next assignment, which I'm still working on, by the way, I'll try and give you some interesting applications or some other interesting theorems which are related to this more general Hardy-Ramanujan theorem. But this was actually, this idea, this is not a very, it's not a very difficult idea to understand. But to interpret Hardy-Ramanujan theorem in this way is what, this is a contribution of Turan, okay? And you'll see, I mean, the entire Turan-Kubilius inequality is a study of sums of this form, isn't it? All right. Now, what we do is, so for the remaining part of this lecture, I'm going to switch gears. Actually, not just gears, I'm going to switch the car completely and move to multiplicative functions. Because now we want to study how to obtain mean value estimates, average orders, normal orders. We want to ask similar kind of questions for multiplicative functions. Okay, as I told you, this technically it is a course in probabilistic number theory, but you register for one and get one free. So you also learn analytic number theory in the course. Okay, so now we are going to move towards like what you would consider, typical first course in analytic number theory. So we are going to study about, we are going to move towards the study of multiplicative functions. But before that, we just want to introduce this approach of Dirichlet series and Euler product. So the approach of probabilistic number theory is to study value distribution of arithmetic functions by interpreting them somewhat as random variables. In analytic number theory, the approach is different. We try to study the value distribution of arithmetic functions by looking at certain series, putting them in generating series and trying to study those generating series as analytic functions to check whether they are analytic or not. So here the approach is, you take some arithmetic function and you define the Dirichlet series capital F of S to be equal to summation the infinite series coming from f of n over n to the s. And here we are going to study this for complex variables s. Okay, so when we were looking at the previous probabilistic methods, very often I just talked about real valued functions and told you that the generalization to complex valued functions is immediate. In analytic number theory, we have to be very careful. We can't just say that, oh, whatever is true for real value just goes over to complex value. That's the whole point of this study of analytic number theory. It doesn't. You need to do more work, right? So what we do is, let's just learn some notation that we are going to stick to for the rest of this class. Sigma plus it. I'm going to take a complex number s and write it as sigma plus it, and I'm going to call where sigma is the real part of s and T is the what you call the imaginary part of S. Okay. Now a small distraction. What does this n to the s actually mean for a complex variable? By definition, it is e raised to the s log n, so exponential of this complex variable s log n, right? Okay, so when you have n raised to the sigma plus it, because of the fact that it can now be written as e raised to the sigma plus it log n, which turns out to be sigma log n times e raised to the it log n. From this, suppose you want to derive the absolute value of n to the s. It would be equal to absolute value of this is a real valued number, times absolute value of e to the it log n. So basically absolute of e to the I theta, where theta is some real number, which is just 1. So absolute of n to the s just turns out to be e to the sigma log n, which is n raised to the sigma. So now we study the absolute convergence of these Dirichlet series, and we see that that is of course related to summation of absolute f of n over n to the sigma, where sigma is the real part of S. So depending on where the real part of S lies in your complex plane, we can determine whether the function absolutely converges or not. Okay, so henceforth, so for the next couple of lectures, for the reference of those who are following this course carefully, I will be following Apostles' book, chapter 11, sections 1 to 7. That is the reference for what we are going to study for the next couple of lectures. So, what this tells you is that absolute f of n over n to the s is equal to absolute of f of n over n to the sigma. Okay, and if you have, so sigma henceforth will be the real part of whatever complex number you're taking. If sigma is greater than or equal to sigma sub 0, what does that tell you? It tells you that summation, so absolute f of n over n to the s, first of all, is just absolute f of n over n to the sigma, but sigma is greater than or equal to sigma naught. So this is less than or equal to absolute f of n over n raised to the sigma naught. So if you know that this sum, as you go from 1 to infinity, converges, that will immediately tell you that the function capital, the series, infinite series capital F of S converges absolutely. So therefore, suppose, so this is the observation. Suppose you have the function F of S converging absolutely for some real number S prime, which you can write as a real part plus I times an imaginary part. Okay, then by what we have done above, F of S will converge absolutely for all those S with real part. So the moment you find one complex number where the sum converges absolutely, then to the right of the real part of that complex number, you will immediately know that the sum will converge absolutely. So, to start with, really all you need is one little point where the sum converges absolutely, and therefore, for all these types of series, we often talk about half planes of convergence. Okay? So, half planes of absolute convergence, I mean. So, what all this tells us is the following. Suppose you have an arithmetic function and a Dirichlet series. By the way, I am not sure if I mentioned it explicitly. This all this that we are studying follows from Dirichlet's proof of the infinity of primes in an arithmetic progression. So, these type of series where you essentially consider generating functions corresponding to an arithmetic function, these are called Dirichlet series. Okay, in particular, when f of n is equal to 1 for every n, you just have the Riemann zeta function. And the study of these series, the systematic study of these types of series for complex variables is the genius of Riemann, as I had mentioned before. So, here is a theorem. Suppose you have some Dirichlet series and you know that it does not converge on the entire complex plane, but it does not diverge on the entire complex plane either. That means it has some points where it converges and some points where it diverges. The previous observation that we just wrote shows that if it converges absolutely at some point, then to the right of the real part of that point also it must converge absolutely. So, this theorem is just making that notion precise. So, suppose the series, now we'll be talking about absolute convergence of these series. So, absolute f of n over n to the sigma does not converge, or so let us take, let us say that this does not converge for all S in C and does not diverge either for all S in C. In this case, what you have is you can find some real number some sigma a in R such that for all sigma greater than sigma sub a, this series will converge absolutely, and for all sigma less than sigma a, the series will diverge. Okay. So, so such that for all sigma greater than sigma sub a, okay, this series over n to the s converges, and for all sigma less than sigma sub a, this series diverges. Very straightforward proof which will follow from the previous observation. Okay, so I will leave it as an exercise. Here are some quick examples. This is one of our most favorite functions, the Dirichlet series corresponding to the arithmetic function which just takes the value 1 everywhere. Okay. Now, what do you know? Summation 1 over n to the sigma, it converges when sigma is greater than 1, and for sigma less than 1 it diverges. So, here we have the sigma sub a. Okay. This is the formal name for sigma sub a is the abscissa of absolute convergence. Okay. So, in this case this is just 1. Sometimes you need not know exactly what sigma sub a is, but it is enough to know like a lower bound for sigma sub a or an upper bound. Okay. So, for example, so next, suppose I have some function f of n. Okay, it can take complex values, but we know that absolute f of n is less than or equal to some m for all n. Okay, in that case, summation absolute f of n over n to the s, okay, is certainly less than or equal to m times summation 1 over absolute n to the s, which is just 1 over n to the sigma, and we know that this is finite whenever sigma is strictly greater than 1. Okay, and therefore this tells us that your sigma sub a, whatever the number is below which to the left of which your series diverges, the series of the absolute values, and to the right of which it converges. Okay, from this it is, we don't know whether sigma sub a is exactly equal to 1. All that we know is that sigma sub a is less than or equal to 1. Okay, let me give you another function that we have seen in our course. Let us take f of n to be equal to the divisor function, or the function that counts the number of positive divisors of n. What can you say about the summation d of n over n to the s? Now recall, d of n is O of n raised to the epsilon for any epsilon greater than 0. And so, suppose we take summation n going from 1 to infinity absolute of d of n over n raised to the s, okay, which in turn is summation n going from 1 to infinity. Since this is a positive function, the numerator just remains d of n, the denominator becomes n raised to the sigma. You are saying that for any epsilon greater than 0, d of n is less than n to the epsilon, and therefore this is n going from 1 to infinity 1 over n raised to the sigma minus epsilon. It converges absolutely when sigma minus epsilon is greater than 1. So, capital converges for sigma greater than 1 plus epsilon for any epsilon greater than 0, however arbitrarily small you want to take it. From this, you deduce that the abscissa of absolute convergence for the Dirichlet series corresponding to the divisor function has to be again less than or equal to 1. Okay. And in general, suppose you have a function f of n, which is O of n raised to the theta for some fixed theta, okay, which is positive, or actually just if it is O of n to the theta for any real number theta, suppose you have this O estimate, then the abscissa of absolute convergence has to be less than or equal to 1 plus theta. Okay. So these are some immediate examples. Basically, what this theorem was saying was, suppose you have, let's say this is your complex plane. Okay, the x-axis denotes the real part, y-axis denotes the imaginary part, and what this is saying is that you can always find some sigma a such that to the right of this your fs converges absolutely, and to the left it does not. Okay, and therefore for any such Dirichlet series there is always a half plane of absolute convergence. This is what it is called, half plane of absolute convergence. Okay, so another important theorem that we have is the following. Just like there is a half plane of absolute convergence, there is also a half plane of non-vanishing. This is also extremely important for us. So here is the observation. Here is a short lemma. And it states the following. Suppose you have some natural number and you have your, so henceforth what we do is we just assume in our notation that you have an arithmetic function, you have f of s which is the Dirichlet series corresponding to that. This converges absolutely for any complex number s with sigma greater than sigma 0. Okay, so this is a notational a notation that we will assume for all the Dirichlet series. Sigma sub 0 is such a point so that to the right of it the Dirichlet series converges absolutely. So now suppose you have n is greater than or equal to 1 and you have any complex number whose real part is bounded below by some absolute constant c, which in turn is strictly greater than sigma 0, then summation as you run from capital N to infinity of f of n over n to the s, this will be less than or equal to 1 over n times sigma minus c times summation of n going from 1 to infinity absolute f of n over n raised to the c. This is always true. Okay, again by this the sort of comparison test kind of a thing you can prove this. So I will leave the proof of this lemma as an exercise, but what is it good for? What is it actually telling us? So this leads to a very nice application which tells you the following, that suppose you take your Dirichlet series, okay, f of s where s is sigma plus it, then the amazing thing is that as sigma goes to infinity, this will have a limit, and in fact the limit will turn out to be exactly equal to f of 1. Okay, and why is something like this true? So what we do is we write our f of s. This is our Dirichlet series. Let me just take the term corresponding to n equal to 1 out, and let us write n going from 2 to infinity f of n over n to the s. Okay. Now the good thing is, so the absolute value from 2 to infinity, so what is the previous lemma telling you? This is less than or equal to 1 over 2 raised to the sigma minus c times over n to the c. Okay, this converges, right? So this is less than 1 over 2 raised to the sigma times 2 raised to the c times some absolute number capital A, since this sum is converging. Okay, and this A does not depend on sigma at all. It depends on just it's this value at c, where all that we need to know is that this sum converges. This limit is finite. So what do you have? You have the absolute value of the second part is less than 2 to the c times A over 2 to the sigma. But then as sigma goes to infinity, this is 0. And therefore, everything from 2 onwards, if you have a sum that is absolutely converging to 0, that sum itself is converging to 0. So this is going to 0, and you are just left with f of 1. Okay, so this is a very nice and amazing fact, very easily proved about Dirichlet series, because of the fact that they have a domain or a half plane of absolute convergence. You are able to deduce that if you take f of s and just let the real part go to infinity, the limit would be equal to f of 1, and this limit is uniform in t. Irrespective of what t you choose, you will still get this. Okay, so this was our discussion of half planes of convergence. One other fundamental observation that I'd like to make before we conclude for today is that, as I just mentioned, there is a half plane of non-vanishing. Okay, so I'll just state that and maybe leave it as an exercise, and perhaps this is something that we can discuss next time. So here is the situation. Suppose you have capital F of s, okay, is this Dirichlet series, and you know that f of s prime is not equal to 0 for some complex number s prime, okay, where the real part is greater than the abscissa of absolute convergence. So that means in the half plane of absolute convergence, there is some point where this function does not vanish. And to have one point, from one point where the function does not vanish, you can deduce an entire half plane where the function would not be identically 0. So in fact, so what I mean to say is that there would be an entire half plane where the function would be non-vanishing. So there is a half plane lying inside the half plane of absolute convergence, such that capital F of S is not equal to 0 in this half plane. Real part of S. So there is a half plane of absolute convergence, follows very immediately from basic complex analysis. And then there is also a half plane of non-vanishing, which is very important for us. We will discuss a proof of this theorem in the next class, and I will stop for today.